Good morning. In yesterday's lecture, we were discussing the chain of oscillators. We had a chain of radiators, each of which was fed an oscillating signal. Each radiator we refer to as an oscillator. This radiates in all directions, and the total radiation received by a distant observer at an angle theta is the sum of all of these radiations, sum of all the waves emitted by all of these oscillators. So, we had calculated the directional dependence, the theta dependence of the radiation that comes out, and we had found that there will be maximas, primary maximas, whenever this condition d sin theta is equal to m lambda. M could be any integer 0 plus minus 1, 2, 3, etc. Whenever this condition was satisfied, there would be a maxima in the radiation that is received. In other directions, you would receive much less radiation. The intensity pattern of the resultant radiation intensity pattern looked something like this. You had these primary maximas. Whenever these are satisfied, whenever d sin theta is equal to m lambda, and this is the primary maxima corresponding to m equal to 0, this is m equal to 1, 2, minus 1, etc. And the width of these primary maximas goes down as you increase the number of oscillators. So, if you have 5 oscillators, this is the width. If you have 20, the width has gone down. In between these primary maximas, you have n minus 1 minimas, where n is the number of oscillators, and you have n minus 2 secondary maximas, which you can see here. These are much smaller in intensity. So, most of the radiation from those oscillators goes out in the primary maximas. And this is the width of the primary maxima. It is delta theta is equal to lambda by d. D is the spacing between the oscillators, n is the total number of oscillators, and cos theta m. Cos theta m is the angle corresponding to the maxima you are looking at. We had also considered the situation where you put a phase difference between two consecutive oscillators, and if the phase difference is 2 phi, if the phase difference is 2 phi, then you find that what happens is that you have to, in addition to the phase due to the path difference, you also have to add this, and what it does is it shifts the angle corresponding to the maxima, and the shift in the angle, the shifted angle is in this situation the maxima satisfy this condition. There is a term involving phi which appears over here. And then in the last class I had given you a problem, and I had asked you to attempt this problem. So, let us now take up this problem and discuss its solution. So, in this particular problem, we have a chain of 100 dipole antennas, each at a spacing of 1 meter, emitting radiation at a frequency of 150 megahertz. So, let me draw a picture over here and explain what this thing looks like to you. So, you have these 100 dipole antennas. Let me just draw a few of them. They are all at a spacing of d, where d equal to 1 meter. You are also given the information. So, n is okay, before that n is equal to 100, we have 100 antennas. We are also given the information that this radiation is at 150 megahertz. 150 megahertz, let us calculate the wavelength, that is what we need. So, the wavelength is c, the speed of light, 3 into 10 to the power 8 divided by 150 into 10 to the power 6, which is 2 meters. So, the wavelength is 2 meters, and the angle theta is measured with respect to this direction. The dipoles are all, the chain of dipoles is aligned like this, and this is the angle theta. Now, before we take up the solution, let me just remind you, if I had a dipole like this, that is vertically upwards like this, then its radiation would be such that it would radiate maximum in the plane over here, and it would radiate equally in all directions on the plane. So, for a single dipole, let me draw the picture here. A single dipole like this, pointing vertically like this, emits maximum radiation in the plane of the paper, and it emits equally in all directions. This is for a single dipole. On the plane, it emits equally in all directions. It does not emit anything in this direction or this direction, and the intensity changes as sine squared theta. We all know this when we have studied the dipole radiation pattern. Now, in this particular problem, we have 100 such dipoles aligned in a chain. So, individually each dipole emits equally in all directions, but now we have 100 of them all being fed the same signal. So, now from the analysis that we have done, we know that the radiation pattern is not going to be the same in all directions. There are going to be maximas and minimas. The maximas are going to occur whenever d sine theta is equal to m lambda. So, sine theta is equal to lambda by d into m, which in this case lambda is 2 and d is 1. So, in this case sine theta is equal to 2m, and m can have any value 0, plus minus 1, 2, plus minus 2, plus minus 3, etc. So, the question is, what are the possible solutions for theta? In this particular case, you see lambda by d is, this is the ratio lambda by d. In this particular case, lambda by d is more than 1. If lambda by d is more than 1, there is only one possible solution, which is m equal to 0, which implies theta equal to 0. So, there is only one solution in this case. All the intensity, all the radiation comes out in this direction. This is the direction of the maxima. Equivalently, sine theta equal to 0 also has a solution, theta equal to pi, which is the backward direction. So, what we see is that when we have only one dipole, it emits radiation equally in all directions in the plane, but now when I have an array of 100 of such dipoles, the radiation pattern has maximas. In this case, there is only one maxima in the forward direction and one in the backward direction. So, the bulk of the radiation goes out towards the direction theta equal to 0 in the forward direction, in the backward direction theta equal to pi. And so, you have been able to introduce a definite directional dependence in the radiation from this whole configuration. Now, let us take up the next question, the next part of the question. Okay, we have already addressed two of the first two parts of the question, that is, in which direction is the intensity, maximum intensity, how many maxima are there, there is only one, and then we have the width of the maxima. To consider the width of the maxima, and we had found that the width delta theta corresponding to the mth order maxima is lambda by d n cos theta. So, in this particular problem, we have the 0th order maxima. So, m is equal to theta m is equal to 0. So, we have delta theta is equal to lambda by n d. So, what we find is that the radiation pattern from this array of dipoles. Let me draw the picture for you over here again. So, we have this array of dipoles like this. The radiation pattern from this array of dipoles is like this. So, it emits most of the radiation in either the forward direction or the backward direction, and it in this particular case it is towards the angle theta equal to 0, and it has a width in angle. The width is lambda by n d, where d is the spacing and n is the number of dipoles in the array. In this case, this n d is actually the total length spanned by this chain of oscillators. So, now let us go back to the problem that we were discussing. We have another part to this problem that we are discussing. So, let us go back to the problem that we are discussing. The other part which remains to be addressed is that what happens when there is a phase difference of pi by 8 between the oscillators. So, remember in the last lecture we had also discussed what happens when you have a phase difference of 2 phi between any two successive oscillators, and in this, so in this particular case 2 phi is equal to pi by 8 or phi is equal to pi by 16. So, the condition for the maximas is sin theta is equal to lambda by d, which is 2. See, the condition for the maxima now gets changed because of this phase difference, and the condition now is sin theta is equal to lambda by d into m minus phi by pi. Phi we have already calculated it, it is pi by 16. So, the maximas now get shifted, and the maximas will occur whenever the condition this is equal to m minus 1 by 16 is satisfied. So, we can see that the maxima will now occur at an angle which is sin inverse minus sin inverse 1 by 8. So, if you introduce a phase between each of these antennas, each of these dipoles, what you do is you can shift the direction in which the maxima occurs. In this case, it will shift it downwards like this. So, by introducing different phases, you can shift the direction in which the maximas occur. So, let me just recapitulate for you the implications of what we have just discussed. We have an array of n dipoles, each at a spacing d. In the situation where I had a single dipole, it would emit radiation equally in all directions in the plane perpendicular to the dipole. In the situation where we have 100 of them, there is considerable amount of directivity in the radiation that comes out, directionality in the radiation that comes out, and in this particular case, when all the dipoles are oscillating at the same phase, the bulk of the radiation comes out in the direction perpendicular to this chain, and it is spread over a small angle delta theta, which is lambda divided by n d, where n d is the total, n is the number of oscillators in the chain and d is the distance between them. So, if the total chain of oscillators span this distance, it is essentially lambda divided by this distance, the largest separation between the oscillators. So, all the radiation gets concentrated into this small angle, and if I introduce a phase difference between the dipoles, then I can make the direction of the maximum move around. So, you see this is what is called a phased array, and this has got tremendous amount of applications. So, let me show you a picture first of a ship. So, the picture here shows a ship, and notice that on the ship you have these rods, these vertical rods. I do not know if you can see them. but there are these vertical rods over here. So, in case you cannot see them, let me reinforce them for you over here on this picture. So, you have these vertical rods like this, and these rods are essentially dipoles. So, each rod over there is a dipole, and if we had only a single dipole, it would emit radiation equally in all directions in the plane perpendicular to the dipole. So, it would radiate emission equally in all directions like this. But now we have an array of dipoles. So, if the same signal is sent to all of these dipoles, the radiation will be maximum in the direction perpendicular to this chain. So, it will come out forward. So, the maximum radiation will come out like this, and if I give a phase difference between all the dipoles, then we can change the direction in which the maximum radiation comes out. So, this can be used as a radar, and you can send out the signal and you can receive the signal that gets reflected back from any source, from any distant object, and this can be used as a radar, and you can make the radar sweep around the whole plane by providing appropriate phase difference between the dipoles and then slowly changing the phase difference. So, if you give a phase difference between the dipoles, then you can change the direction in which you have the maxima, and if you change the phase difference between the dipoles, you can make the direction of the maxima slowly sweep the whole sky like this. And this can act like a radar. So, this is this phased array has got applications as a radar, as you can see on this ship here. So, this is a battleship, and on this battleship the phased array acts like a radar system. So, you can there are various other applications. So, let me show you another application of the phased array. So, the next application shown over here is an array of phased arrays. Now, we had already seen in earlier lectures that if you want a dipole to be effective in sending out radiation, the length of the dipole should be comparable to the wavelength at which you are radiating. So, if you are working at something like 1 meter wavelength, then the dipole should be also of length 1 meter, which is what the situation that I had shown you just a little while ago. The radar on the ship, that was possibly working in somewhere like a wavelength, maybe a few centimeters, and the length of the dipoles were also of the order of meter, maybe a few centimeters or a meter. Now, if you go to much smaller wavelengths, let us say millimeter wavelengths, so lambda is of the order of millimeter or possibly even less. This wavelength, this has got several satellite communication, and various other communication applications. So, orders of the wavelengths of the order of from centimeter to millimeter. Then the radiating elements will also be smaller, and this picture shows you an array of phased arrays. So, this shows you an array of phased arrays, and this is on a much smaller length scale, as you can see. Now, each of these, so this is one phased array. Using a phased array, you can ensure that the radiation gets directed in a particular direction, and you can change the direction by introducing different phases between these radiating elements. And using an array of such periodic phased arrays. So, you have one phased array over here, you have another phased array over here. So, you have a array of phased arrays. Using an array of phased arrays, you can actually move around the direction of the radiation in both this direction and this direction. So, both horizontally and vertically. This gives you 2 degrees of freedom in which you can turn the direction in which the majority of the radiation comes out. Let me now show you another application of the same idea of a phased array. So, so the picture which I am going to show you now is an application in radio astronomy. We had discussed the cosmic microwave background radiation much earlier, and there is a considerable amount of effort going on to map the cosmic microwave background radiation at high angular resolution. So, this picture shows you, this is a picture of the Arcminute Microkelvin imager. This is at Cambridge, UK. It works in the frequency range 12 to 18 gigahertz, and it has got antennas which you can see over here. There is a linear chain of antennas. A part of the array of the Arcminute Microkelvin imager is a linear chain of antennas which you can see over here. Each of these antennas is 13 meter in diameter. So, the question is, what is achieved by having a linear chain of antennas over here? So, let me just spend a little time discussing this point. Each antenna, let us say that we are working at 15 gigahertz. So, if at 15 gigahertz, let us first estimate the wavelength. So, the wavelength corresponding to 15 gigahertz will be 3 into 10 to the power 8, this is meters per second, divided by 15 into 10 to the power, gigahertz will be 10 to the power 9 per second. So, this gives us lambda . So, 10 to the power 9 over here, 10 to the power 8 over here, which gives us a factor of minus 10 to the power minus 1 already, and then if I divide 3 by 15, I get 2 into 10 to the power minus 2 meters. So, this is the wavelength, it is 2 centimeters. And in this particular situation, we have antennas of diameter d, which is 13 meters, and we have studied a few lectures ago that because of diffraction, the diffraction is going to set the angular resolution of these antennas. So, the angular resolution of these antennas is of the order of lambda by d. Lambda here is 2 into 10 to the power minus 2, d is 13. Let me just take it to be 10 for simplicity to get an order of magnitude. So, lambda by d, the angular resolution is 2 into 10 to the power minus 3 radians, and to convert this into degrees I have to multiply it by 2 into 10 to the power minus 3 into 180 divided by pi, which I can take of the order of 60. So, this gives me 1.2 into 10 to the power minus 1 degrees. Right. So, that is the kind of resolution, angular resolution of this 0.12 degrees is the kind of angular resolution of lambda of the of this single antenna. So, each of these antenna, if I had one antenna like this, it would receive radiation it would emit radiation or receive radiation from an angle of the order of 1.2 into 10 to the power minus 1 degrees. Now, what is the advantage if I combine a set of antennas like this in the form of a phased array? We have seen that if I combine these radiating elements as a phased array and I do not give any phase difference between two of the consecutive elements, then it is going to emit the maximum radiation in the forward direction, assuming that there are no other maximas. If there are other maximas, there will be other directions also in which you will have primary maximas, other primary maximas, but let us focus on the primary maxima which is in the forward direction, m equal to 0. So, it is going to emit bulk of its radiation in the forward direction, or it is going to equally receive bulk of the radiation from the forward direction, and from a width delta theta which we have seen is going to be lambda by Nd, where Nd is the spacing, is the total, d is the spacing between any two of these oscillators, and n is the total number of oscillators. So, with reference to this particular picture, let me tell you what is going to happen. What is going to happen is that one of these antennas, so each of these antennas we have seen is going to emit, if I had only one antenna, it would emit radiation or receive, it would have a resolution which is 0.12 degrees. But now when I have when I use this as an array, its resolution is going to be decided by this total length over here, and the resolution of this is now going to be of the order of lambda into L, lambda by L instead of lambda by d, and this number is going to be smaller. So, you will be able to achieve a higher angular resolution, a smaller angular resolution when you use this chain of antennas as an array instead of using them as individual antennas. That is the crucial point, and the angular resolution is going to be decided, as you can see, the angular resolution is going to be lambda by Nd, that is the width of the primary maxima. So, that is going to be the angular resolution. It is going to be decided by the separation between the two furthest elements in this chain of oscillators. Let me now discuss another application of this chain of oscillators which we had discussed in the last class, and this particular application is what is called a diffraction grating. A diffraction grating is essentially an opaque screen. So, we have an opaque screen over here. In this opaque screen, you have a periodic arrangement of slits which you can see over here, and the spacing between any two slits is d, any two successive slits is d. So, if I draw a picture for you here, it will be clear. So, if you look at it face on from the front, it will look like this. You have this opaque screen on which you have a periodic arrangement of slits. So, each of these is a slit, and you have a plane wave incident on this diffraction grating. So, when a plane wave is incident on this, each slit acts like a source for a secondary wave. So, each of them now emits a secondary wave, and this is effectively a chain of oscillators because you have the same radiation coming out from each of the slit. Before going on to discuss what the intensity pattern will look like, let me discuss how you can construct a diffraction grating. You might have seen a diffraction grating in your physics laboratory. They are typically if you are working in the optical range, you will find that what the diffraction grating will be something of this size, and if you look at it, you will notice that there are these dark lines and through which the light cannot pass, and then there are these transparent lines through which the light can pass. It will look like this. So, one way you can realize this kind of an arrangement is if you draw black and white lines, if you paint black and white lines on a wall. So, take a wall, a big wall, and paint black and white lines on this wall. It is on a large scale, a big wall, paint black and white lines. Now, take a picture of this using a camera, go to a distance and take a picture of this using a camera and take the negative. You develop the film, you will get a negative. In that negative, you will have a transparent region. The negative will be the inverse of the picture that you have taken. So, corresponding to the black line, you will get a transparent region, and corresponding to the bright line, you will get a dark region, and you will have this black and white rulings on your negative, which you can use as a diffraction grating. It is going to essentially be a very scaled down version of the black and white lines which you had drawn on the wall. There are many other possible ways in which you can construct a diffraction grating. The diffraction grating, so the question now is, what is the intensity pattern that the diffraction grating is going to produce on a screen over here? The intensity pattern that the diffraction grating is going to produce on the screen over here. Let me write down the expression for you. The intensity pattern that the diffraction grating is going to produce is given over here. It is I equal to I naught sinc square n alpha divided by sin square n alpha into sin square n alpha divided by sin square alpha into sinc square beta. So, you see the intensity pattern produced by the diffraction grating is a product of three terms. The first term is the overall intensity. The second term is the intensity pattern produced by the chain of oscillators. Here alpha is pi d sin theta by lambda. D is the spacing between each of the oscillator in the chain of oscillators, and we have another term which is sinc square beta, which again you must have encountered in this course a few lectures earlier. Beta is pi d sin theta by lambda. So, this d is the separation between the slits. So, the grating that we have is a sequence of slits which are equally placed. The separation between any two slits is d, and the width of each slit itself is capital D, and the intensity pattern which this diffraction grating produces is a product of the intensity produced by a chain of n oscillators, each at a separation small d, multiplied by the intensity pattern produced by a single slit of width capital D. So, the next question is, what does this intensity pattern look like? So, we will consider a situation where capital D, the slit width, so the width of each slit is much smaller than the spacing between the slits. So, we will consider this situation, which is the situation that occurs usually in a diffraction grating. So, we will consider a situation where each slit width is smaller than the spacing between the two consecutive slits. Now, in this situation, let us ask the question, if I vary theta, which of these terms is going to change faster? And it is quite clear that since this slit width is much smaller than this spacing between the slits, this term alpha is going to change much faster and this term beta is going to change much slower. So, the intensity pattern due to the chain of oscillators is going to change much faster. The intensity pattern due to the diffraction pattern of a single slit is going to change much slower, and this is what determines the overall final intensity pattern produced by the diffraction grating. This is what is shown over here. The intensity pattern produced by the chain of oscillators, this changes much faster as we have just seen. This decides the intensity pattern by the chain of oscillators. This d, the spacing is much bigger than the width of each slit. So, this is going to change much faster. This is what you see here. The contribution, the pattern due to the chain of oscillators is much more rapidly varying. You have this primary maxima, then you have a minima, then you have a secondary maxima, you have quite a few secondary maxima, you have another primary maxima of a higher order. Again you have these secondary minimas, maximas, again you have another primary maxima of a higher order, and so forth. This is multiplied by the diffraction pattern of a single slit, which is shown by the dashed line over here. This varies more slowly. The net result of this whole thing is as follows: if the slit width were ignored, then all the primary maximas would have the same intensity. This was the situation that we had considered in the last class. All the primary maximas would have the same intensity, which would be I naught n squared, where n is the number of oscillators. But because of the effect, the finite width of the slit, the higher order maximas are going to have a smaller intensity. So, the m equal to 0 order is going to have the maximum intensity. As you go to higher order of m, the intensity of the maxima is going to fall, which you can see over here. The first order m equal to 1 intensity is considerably smaller than m equal to 0. M equal to 2 cannot be seen at all because it falls very close to the minima of the diffraction pattern of the single slit. M equal to 3 can barely be made out over here, and the others will be quite small. So, what we see is that we have both the effects in a diffraction grating. We have the chain of oscillators. The chain of oscillators produces intensity pattern with many maximas, many possible maximas, all of the same intensity. But if you take into account the fact that each of the slit has a finite width, then this gets multiplied with the diffraction pattern of a single slit, which is a sink square function, and this causes the higher order maximas, that is m equal to 1, 2, 3, these to have more and more, to the intensity of these maximas to become progressively fainter and fainter, which is what you see over here. So, this is the intensity pattern predicted for a diffraction grating. Now, the diffraction grating is a very useful device in spectroscopy. Its utility lies in the following: the maximas we know occur wherever this condition d sin theta is equal to m lambda. Whenever this condition is satisfied, we get a maxima. Now, if I have two different wavelengths, so if I have lambda 1, the maxima will occur at theta 1. If I have lambda 2, the same order maxima will occur at a different angle theta 2. So, if m is not equal to 0, if m equal to 0, then all the maximas independent of wavelength, for all wavelengths the maxima occurs at theta equal to 0. But if m is not equal to 0, the angle theta at which you will get the mth order maximum depends on the wavelength. and if you have two different wavelengths, the maxima will occur at two different angles theta, and you can use this to determine the spectral composition of light. So, if I have light which has got several wavelengths, I can send this light into a diffraction grating. So, if I send light of different wavelengths into a diffraction grating like this, the 0th order maxima for all wavelengths will be at theta equal to 0, but the first order maxima, let us say, will occur at different wavelength, different angle theta for different wavelengths. So, for a wavelength lambda 1, let us say it occurs here, for a wavelength lambda 2, it may occur at a different angle, it will occur at a different angle. For wavelength lambda 3, it will occur at a different angle. These are all m equal to 1, and m equal to 2 will occur elsewhere, and so forth. So, this allows you to determine how many different wavelengths there are in the light that you are sending in, and this plays a very important role in spectroscopy. So, this is what spectroscopy is all about, to determine the frequency components that are present in the light that you wish to analyze. So, this property of a grating is quantified through what is called the dispersive power of the grating. So, the question is as follows: we have light of a wavelength lambda, it produces a maxima, mth order maxima at an angle theta. Now, at an angle theta m. So, this is lambda, it produces mth order maxima at an angle theta m. Now, instead of lambda, if I have a wavelength lambda plus delta lambda, it is going to produce the maxima at a different angle. Let us call that theta m plus delta theta m. So, the question is, how much is this delta theta m? So, the maxima we see occurs at whenever this condition is satisfied, d sin theta is equal to m lambda. So, delta theta can be calculated, the shift in the maxima can be calculated by differentiating this and multiplying it with delta lambda, and if you differentiate this expression, what you get is d cos theta d theta d lambda is equal to m lambda. So, d theta d lambda is equal to m lambda by d cos theta, this is equal to m lambda by d cos theta m. This is called oh sorry, this lambda will not be there. When I differentiate with respect to lambda, this lambda is going to vanish, and this is going to give me 1 basically, and this is the condition. And this term in the brackets is what is called the dispersive power of a grating. What it tells us is that if I put in light of wavelength lambda, the maxima will occur at an angle theta m. If I change the wavelength by a small amount to lambda plus delta lambda, how much is the maxima going to shift? The maxima is going to shift by an amount which is proportional to delta lambda, and this constant of proportionality is d theta d lambda. This is what is called the dispersive power of a grating. It tells us that if I change how much the angle is going to shift, angle at which the maxima occurs, how much this is going to shift if I change the wavelength by a slight amount. Let us take another quantity which is of interest when we use the diffraction grating as a spectroscopy. So, there is another quantity which is of interest when we use the diffraction grating as in spectroscopy, and this quantity is called the chromatic resolving power. as follows. We have light of two wavelengths, one lambda and another lambda plus delta lambda. The mth order maxima of the wavelength lambda occurs at a particular angle theta. So, this shows you the mth order maxima corresponding to a lambda wavelength lambda, it occurs at an angle theta, and for the wavelength lambda plus delta lambda, the maxima is shifted by an angle delta theta, where we have just calculated how much it will be shifted, and we saw that it will be shifted by an amount which is m divided by d cos theta m into delta lambda. So, for the wavelength lambda plus delta lambda, the maxima is going to be shifted by this amount. Now, the question is, under what condition can we say that there are two different wavelengths and not one? So, this is what is called, referred to as the two lines, two different spectral lines, two different wavelengths being resolved. So, there are two different spectral features over here. In order to say that we can resolve these two spectral features, the shift in the angle should be such that the maxima of this wavelength lambda plus delta lambda coincides, at least coincides, the shift is sufficient so that it at least coincides with the minima of the intensity of the wavelength lambda. So, this shift should be sufficient, should be such that this at least coincides with the minima of this. If it is more, if the shift is more than the minima, then you can distinguish between this curve and this curve, but if the shift is less than the minima, you cannot distinguish between this curve and this curve. That is the Rayleigh resolving criteria. So, we can resolve these two lines, these two wavelengths, provided the shift in the angle is more than the minima of this particular curve. And we have calculated where the minima of this curve should occur. The minima of the intensity profile of the diffraction pattern corresponding to a wavelength lambda, that will occur at an angle delta theta. The the minimum will occur at lambda divided by n d cos theta m. So, this is where the minimum will occur. This is the minima of the wavelength lambda, and the maxima of the wavelength lambda plus delta lambda is going to be at delta theta is equal to m divided by d cos theta m into delta lambda. So, the Rayleigh criteria for resolving these two different to be able to distinguish, to be able to resolve these two, is that this should be equal to this, only then can you resolve these two different spectral features. So, if I equate these two, it tells me, let us see what it tells us, lambda by n d cos theta m is equal to m delta lambda by d cos theta m. So, what it tells us is that delta lambda is equal to lambda divided by n m, or so, this is how the chromatic resolving power is defined. If I have two different spectral lines, so if I have a radiation which has two different wavelengths at a so the wavelengths are at around the wavelength lambda and they are separated by delta lambda. For example, remember sodium has two different wavelengths, 585890 Armstrong another at 5896 angstrom. So, the question is, under what condition shall we be able to distinguish that there are two different wavelengths and not one? We have worked out the condition. If this condition is satisfied, we shall be able to say that there are two different wavelengths and not one. And for a grating, there is this quantity called the chromatic resolving power, which is defined as the ratio of lambda by delta lambda, which for a diffraction grating is the number of slits into the order of the maxima that you are looking at. So, the number of slits that you have in your grating into the order of the maxima that you are looking at, this decides the chromatic resolving power. The larger the chromatic resolving power, the better is your diffraction grating, right, and the smaller the chromatic resolving power, the less is your diffraction grating. The chromatic resolving power is essentially the inverse of the ratio of the separation that you can distinguish divided by the value of the wavelength around which these two wavelengths are distributed. So, this is how you can quantify the chromatic resolving power, the ability of a grating to distinguish between two different wavelengths. So, in yesterday's lecture and today's lecture, we have been essentially studying the radiation from a chain of oscillators or a periodic arrangement of oscillators. So, whenever we have a periodic arrangement of radiation sources, we get the kind of diffraction pattern that we have been discussing over here. So, all of this that we have been discussing is all valid whenever we have a periodic arrangement of radiation sources. In the next lecture, we shall take up another very interesting application. In today's lecture, we took up several applications of this chain of oscillators or a periodic arrangement of radiating sources. We had the phased array, which can be used as radar, which can be used several applications in communication, radio astronomy, and then we considered the diffraction grating, which is also a periodic arrangement of radiation sources. And in tomorrow's lecture, we shall take up another periodic arrangement of radiation sources, and this particular periodic arrangement occurs in nature. So, that we shall take up in the next class tomorrow, which is the next class. Okay.